Hello, everyone. Thank you for inviting me, and thank you for organizing this talk. And I'll be talking today about the topic of trustworthy machine learning. I believe this is a very important topic, and I think that usually um, research and applications are more focused on how to get the best performance. For example, how to get the most accurate image classifiers, or how to get um, the best language models, the most accurate um, uh, translation models. And this, all these applications, all this research tends to forget about the very critical trustworthiness aspects. And what I mean by the trustworthiness aspects in machine learning are all the aspects that make machine learning algorithms reliable. For example, privacy. By privacy, I mean essentially that the data used to train machine learning algorithm is not disclosed, is protected against any kind of violations, and that what I mean by robustness is that the training algorithm is not vulnerable to corruption, to data poisoning or the likes. I'll go into more details, but hopefully by the end of this talk, you'll be convinced that it's not only important to have good performance, it's also very important to satisfy those requirements of trustworthiness, and most importantly for me, robustness and privacy. So let me first recall some important points on machine learning algorithms. In general, what we mean by machine learning algorithms are algorithms that we do not need to program explicitly to perform certain tasks. For example, if you think of this MNIST database of handwritten digits, we want an algorithm that can recognize, can classify these digits properly without getting an expert to hard code specific rules for image classification or digit recognition. As most of you know, there has been a tremendous popularity rise of machine learning algorithms, deep learning algorithms, because of the large amounts of data that are available, and these amounts are actually increasing. And same goes for the computing power that enables us to train very complex models. And typically, to devise our training algorithm, we need to be able to quantify what's a good machine learning model. And for example, if you think of just a binary classification task, we'll say that a model H parameterized by theta is good if it has a low error on some training set D, and this translates as loss function L theta. So you know that you have good parameters if the loss function L at theta is small. And to improve your model or your parameters, you can use many different optimization algorithms. The most interesting one for practical purposes are the gradient-based methods. So typically in gradient descent, we have a loss function that you want to minimize. You simply evaluate the gradient at the current parameters. Then you take a step in the opposite direction of the gradient because you're sure that this will locally improve your model. You do this iteratively, obviously, until you get some satisfying model. I will shift now to the to distributed machine learning. Distributed machine learning is a paradigm that enables to train or for multiple machines to train together, to learn together. And this paradigm has also known a rise in popularity in the couple of, in like, let's say, the last 5 years. And one of the motivation is really performance. So given here an example of just YouTube data. So like how much compute is needed to just process YouTube. And YouTube data is really a drop in the ocean of available data. So the interesting thing is that the ratio of data to compute is increasing. Simply do not have enough machines to process all of YouTube. We need the hundreds of GPUs, even the best GPUs produced each year, and this is only increasing, as you see, in exponential fashion. And what this confirms, like the really interesting point, is that it's not possible anymore to train modern models on a single machine. There's not enough compute power. There's not enough memory even, and this is especially true if you think of the large language models trend nowadays, where you have models easily in the hundreds of billions of parameters. And this is only increasing. Actually, the plot doesn't show it, but it's super exponentially increasing. And the amount of compute that it's insanely expensive to train these large language models. And in many cases of these language models, they are trained in a distributed fashions. Otherwise, it's not possible. So this is really the strength of these paradigms, is enabling really another era of complexity in our models, in the machine learning models. Another important motivation is the promise of privacy. So essentially, if you have multiple machines training together, they do not have to disclose their data when communicating with other machines. All they need to share is the actual information that will be useful for training, which are the gradients or the models. Now, gradients or models, they may leak data, obviously, but this is already much better and much more privacy friendly than collecting data and then training them centrally. And throughout the talk, you can simply think of one distributed system, which is sometimes called federated architecture or the parameter server architecture. It's become very, very popular in the recent years. I think at least in the last 5 years, many companies, many large companies they have deployed federated learning algorithms. And the way it works in this system is that you have a central server and you have many machines. These machines, they can be devices, they can be hospitals. And what the server does is that it coordinates the training of these algorithms. And you would typically have iterative machine learning algorithms on this federated architecture coordinated by the central server. Here, this distributed version would just be that the machine locally computes the stochastic gradients or the momentum, etc. And all the server does is that it just aggregates this information and just updates the model using this information. Okay. So, so the question is, what could go wrong this system, in this algorithm. And this is what we're going to think about to establish, let's say, trustworthiness. So there are at least two things that could go wrong. First thing is that some of your workers here, or when I say workers, I just mean the machines or the devices. So some of the workers, they may send corrupt information. I may have a small fraction of these, but for example, they could be computing ingredients on corrupted data. Okay, if you're scraping the internet, you should expect that a lot of the data is actually poisoned, corrupt, or very low quality. So those workers do pose a threat. You may have workers that have simply software, hardware bugs. They just fail to correctly give you the correct gradients. And in the worst case, like when we will want to establish the robustness of a training algorithm, to say that the training algorithm can actually output a good model, even if you have such adversarial workers, we want to think of the worst case. That is, you have a fraction of the workers that are like hacked, that purposefully send you malicious information, malicious gradients, or malicious models to ruin your training, so that you get the worst accuracy, the worst training loss or training accuracy possible. Okay, so that's the first thing that could go wrong. Okay, those are the malicious workers. And the second thing that could go wrong is that some of the workers, they may be curious. And curious is just the technical term in the privacy community to talk about workers which look at the gradients, they look at the models to try to infer private information, to try to infer sensitive attributes of the information. And remember I said how distributed machine learning offers or promises some kind of privacy because you don't have to send the data, you can just send gradients. It turns out that if you just send the gradients and do not add any protection, then your data as a worker can be reconstructed by any entity that can actually eavesdrop, that can listen to the gradients or the models. It's actually there's this work from 2019, so it's quite a while ago now. You can see how well it reconstructs MNIST and other more complex data sets in just a couple hundreds of iterations. In our quest of a trustworthy algorithm, we will be essentially looking for protections against, remember, malicious workers and curious workers. Okay, and we'll go now into the details of what I mean by each of these goals. So first, the first goal, robustness. So here I wrote Byzantine robustness because remember, we want to be able to defend against the worst case adversaries, to claim robustness, to claim trustworthiness. And to do that, we need to have a clear threat model. And this threat model, we need to model, we need to imagine the worst case adversaries. And those kind of adversaries, the worst case in such distributed systems, they're traditionally called Byzantine. This is from the distributed computing literature. And what Byzantine workers are, they are workers that want to ruin, that want to indiscriminately hurt your training algorithm. You should assume that they have full knowledge, meaning they know which algorithm you're using. They know the data, let's say, even of that you want to test on, that you would like to train on. They know everything. They are computationally unbounded, meaning they can execute any algorithm in any amount of time if you want. And they may collude, meaning you should assume that there is a single entity that's controlling a fraction of those Byzantine workers. Okay, so that's really the worst case. And you will see, even in this worst case, we'll get some very good guarantees. Okay. Well, formally, for those of you who are interested, so what we will mean by Byzantine robustness is that if you have F Byzantine workers out of N total workers, we want the average loss on the honest data, which is, so the honest identities here are denoted by age. We want your algorithm to output a model theta hat that has a good loss across the honest data, disregarding anything that the malicious or the Byzantine workers do. Okay, regardless of what they do, we want to ensure that we have a trainer loss that is as small as possible. Okay, and I'll explain that later. But essentially, remember, in distributed gradient descent, what you do is you aggregate the gradients. Okay. Now, if you do averaging, which would be the natural thing to do if you don't care about such Byzantine adversaries, then a single Byzantine adversary can manipulate your average, obviously. They can send a very large gradient, they can send some particular gradient in some direction, knowing that you're using an average. And this will completely ruin even the first iteration of any training algorithm. So what you need to do instead of using averaging is you need to use some sort of robust aggregation. Okay. So the simplest thing you can think of is that to aggregate gradients, you'll go in each coordinate, okay, and then you'll just compute the median of these coordinates. Okay, that's pretty simple thing to do, pretty fast, and it works well as we will see later. Okay, now that's on the aggregation part. And typically, to get such Byzantine robustness guarantees, you will also want to use something that's stronger than simply using SGD. You will want to use something like momentum or more general variance reduction methods. Okay, so that's the first goal, Byzantine robustness. Now the second goal for privacy is differential privacy. This is a widely adopted standards nowadays in the privacy community, and essentially an algorithm in general it's differentially private if you run the algorithm on two adjacent data sets. Adjacent data sets means that they differ only on a single record, or for example, a single image or a single user's text, some unit. They differ on a single unit. If you run your algorithm on these two adjacent data sets, then the output should not be very different. Okay. And the way we will quantify this difference is with statistical distances. So you will say that in some statistical distance, for example, some probabilistic divergence, the difference between the algorithm's outputs in this distance and the other is bounded. Okay. So in terms of probabilities, this translates as the following: if you observe something when running the algorithm in some dataset D prime, then the probability should be more or less the same on your dataset D. Okay, and this more or less that I just brushed right now is quantified by epsilon and delta, and essentially the smaller epsilon and delta are, the stronger your privacy guarantee is. All right. And if you do verify this kind of guarantees, this kind of differential privacy guarantee, then the attack I showed you in the beginning that can kind of look at the gradients and invert and go back to the data, these attacks don't work anymore. So differential privacy guarantees protection against these kind of attacks. Now, once again, this looks like a strong requirement. But it's actually pretty easy to implement, to enforce. The way you do it is that if you want to protect some information, say a gradient, what you will do is that you will just add noise. Okay, you will add, for example, Gaussian noise, and the trick is to choose the variance of the Gaussian noise to be large enough, of course, to verify your privacy guarantee. So let's say, for example, the variance should scale proportionally to 1 by epsilon, let's say. And you want this, if this variance is large enough to protect privacy, this is good. But you also want, for performance reasons, this noise to be as small as possible. You want to reduce this noise somehow. And this is what happens in practice. Or in training an algorithm, you will tune this variance to be the smallest possible to guarantee differential privacy. Okay. Now, remember we said that the adversaries, the privacy adversaries we're trying to defend against, are any entity that can eavesdrop, listen to the gradients. This is actually called the local model of privacy, meaning you don't even trust the server, you don't trust any other entity than yourself in the system. So whatever you're sending, you will add noise to it to guarantee privacy. And this is what I mean here by distributed differential privacy. So it's a stronger model, a stronger privacy model than the usual centralized differential privacy. Okay, so I hope so far the two goals, Byzantine robustness and differential privacy, are clear. Now I will kind of go in depth towards the first goal, Byzantine robustness, and I will explain essentially how one of the most critical aspects when it comes to guaranteeing robustness in distributed machine learning is really the data heterogeneity among the non-malicious workers. And once I'm done with this part, I will explain the trade-off that there is between robustness and privacy. As you will see, you cannot have both simultaneously at any utility. You will have to pay something. So I'll first go through the robustness part. So remember, distributed gradient descent, the way it works is that at each step, the workers send gradients computed in the local data, and then we make an update, a descent update with the aggregate gradient. Okay. Now, it's well studied that if the workers sample data from the same distribution, this algorithm works perfectly fine using almost any robust aggregation you can think of. You can use a median, you can use trimmed mean, you can use geometric median. All of these things work well, and you will get any accuracy, any training accuracy that you want if you do enough training iterations. So the issue really is when the workers do not have the same data distributions. So for example, if we're doing federated learning on using our phones data, this would mean that, for example, I have different images, different labels of images than some other users. We have different style of writing our text than some other users. This is really what's meant here by data heterogeneity. And data heterogeneity is something that happens in the real world, like it's the norm. And the issue really is that if you have data heterogeneity, you cannot distinguish between a malicious behavior and some, let's say, weird, honest behavior, some honest data that is a minority in the global population. You cannot distinguish it from someone who's actually lying or trying to ruin the system. And this is why it was proved that there is a fundamental utility cost, meaning there's a fundamental error that any training algorithm will be paying if you have Byzantine adversaries in a system with data heterogeneity. Okay. So for us to claim robustness, we will need to give theoretical guarantees against the worst case adversaries. Remember the Byzantine adversaries. And to do that, we'll need to quantify heterogeneity in the system. Like we will need to be able to bound heterogeneity and then make conclusions depending on this bound. Now, this itself is a question. It's not entirely clear how do you quantify heterogeneity in the data. Okay. So I'll give here some candidates, and obviously I'll pick the ones that we chose with the paper. But here I'm just explaining why. What's the rationale behind our choice? So essentially, what's a good candidate of the bound on heterogeneity depends on the problem you're trying to solve. And the problem you're trying to solve, the learning task, is in great part determined by what is the regularity of your loss function. Okay, so for example, if you're doing something like linear regression, okay, and the data is regular enough, you add some regularization term, for example, then you will have a nice function, so a nice strongly convex function, and if you have such a good function, then a candidate for a heterogeneity bound is simply heterogeneity at the minimum, meaning it can be, for example, the variance of the gradients at the minimum only, and this would be your heterogeneity bound. Now, why is this a good candidate? Because if your training algorithm could start from the best point possible, could initialize it at the minimum of the loss landscape, then you would want to pay nothing more than the heterogeneity at the minimum itself. So that's really why it's probably the best choice possible. Now, in neural networks and the likes, your loss is probably not convex, is most definitely non-convex. And you cannot have this reasoning anymore because there's not necessarily a single global minimum. Even worse, you cannot hope to reach any minimum at all if you have a non-convex function. It will probably at best only reach stationary points. And so so that's the illustration here. So what can you do in this case? Well, then a natural candidate would be just to have a uniform bound on the variance of the gradients across data sets this uniform bound has to be across all stationary points. As I said, stationary points are the best possible hope in non-convex optimization. And in general, the rationale is just that you should be bound in the heterogeneity where you hope you can possibly get. Okay, so these are our candidates, and actually there are a couple of, for those of you who are interested in federated learning or the theory of federated learning, there are some well-established data heterogeneity bounds. The first one here, the first equation here, you should simply read it as the variance of the gradients across workers has to be bounded across on all the space of models. Or you can say something a little more reasonable, which is to say that the variance is bounded, but may grow proportionally to the average gradient. So this is the average gradient across honest workers. Now, as I explained, the second assumption is something that's very reasonable, but the first one, the one where you say that the variance of the gradients is bounded across all the space, may be true theoretically if you have some very regular, some like data smooth loss function. But essentially, this last equation here, this it kind of subsumes all the candidates I showed in the last page. So essentially, when the gradient is zero, meaning you are at a minimum, for example, for a strongly convex function, then this g squared would simply be the variance at the minimum, right? And this is the best we were hoping for. Now, if you're a non-convex function, you can simply hope to reach stationary points. Then G squared would be the variance across stationary points across the space. So this subsumes really those ideal candidates we were talking about in the last slide. Okay, so this is the assumption we'll be working with, GB gradient dissimilarity. And for those of you who may not be interested in the theory, what you should be thinking about here is that those are two parameters that kind of quantify how heterogeneous the task is, and G simply it kind of just determines how different the data is, while B determines how different the loss functions are. Okay, I hope this is clear. So now we've settled on our our data heterogeneity model, and the question here is how can we obtain tight bounds, and what are actually the tightest bounds possible under this assumption? So those are the main results of the paper, and I won't be listing all of them. We'll be listing the main results. I'm simplifying those results actually, so you can, if you want to go into more details, should look at the paper. So if you use robust DGT on a strongly convex problem, our result is the following: if your fraction of Byzantine workers in all the systems, so the number of Byzantine workers divided by the total number of workers, is small enough compared to 1 divided by 2 plus b squared. Remember, the larger b squared, the more heterogeneity you have. So you have no heterogeneity. This quantity is just 1/2. And it makes a lot of sense to say that the limit of our theorem is just that the fraction of Byzantine is exactly 1/2 in the system. Above this, you cannot hope to get any guarantee. Okay, so we assume this. We assume that if the fraction is smaller in this quantity, then we can show that robust distributed gradient descent asymptotically achieves an error bounded by the heterogeneity at the minimum only. Remember, this is a very good quantity, as I explained earlier. So if you do not have strongly convex losses, if you have smooth non-convex losses, you would get a similar results with the GB gradient heterogeneity assumption. And the interesting part is that this assumption that we made on the fraction is actually necessary. This is something we showed. This is a really strong result. We show that no matter what training algorithm you use, if you hope to minimize or get some convergence guarantees in a system where you have GB gradient dissimilarity, meaning you have data heterogeneity, which can be quantified by our earlier GB gradient dissimilarity assumption, then it has to be that the Byzantine fraction is smaller than 1 divided by 2 plus b squared. Moreover, even if this condition is verified, then you cannot hope to get a better error than this quantity. And this you should simply read as g squared. Remember, g squared, it's in the best case, the heterogeneity at the minimum, amplified by the fraction of Byzantines. Okay, so this is once again, intuitively, from a high-level perspective, if you have Byzantine workers in the system and there is heterogeneity, you will be paying an error that's proportional to the heterogeneity in the system, and that's amplified by the fraction of Byzantine workers in the system. Hope this is clear. And we actually not only show these results, we actually offer some even practical insights on what they mean and what they could, how they can be sensed, kind of. So there are essentially two questions you could ask, even if you have those results. So first, in practice, what are those values? What are G and B? Right? Let's say you show that you get this tightest band possible that's proportional to G squared. How do I know that G squared is not just a gigantic quantity that, and so that your theoretical guarantees have no sense? Okay. And the second question is, those negative results we get, meaning this breakdown points I mentioned, 1/2 plus b squared, is it a realistic one? Is it something that corroborates experimental results? And we give insights into these, and essentially we show that the intuition about G and B is that G is usually very small quantities. It's like the variance at the minimum only. So it's a quite small quantity. And B, once again, as I explained, it's like the difference between the scalings of the loss functions, essentially how different their smoothness constants are. And we do verify that B decides essentially the breakdown point of the system. So if B is too large, then you will not be able to learn anything in the system if the fraction of Byzantine workers is larger compared to 1 by B squared. Okay, so we do verify this. But on only simple problems, obviously, and elucidating any of these questions in more general settings like non-convex and the likes would be very interesting. So so at this stage, I'm done explaining this this paper. So this will appear at the next NeurIPS, and you can already actually take a look at the archive that's available. Now, let me go back a bit on privacy. Now I've explained to you, hopefully, that if you have heterogeneity in your system, then robustness problem is hard. Okay, Byzantine robustness is hard because there is a hard lower bound on what you can hope to achieve in terms of error. Now, this is also the case for privacy alone, like not even considering robustness. If you remember differential privacy, if you want to enforce differential privacy, then it's very probably by adding noise. It must be by adding noise in some way. But for example, it's by adding Gaussian noise. Okay. Now, if you add Gaussian noise, as explained, you incur a loss in accuracy. That's fundamental. And actually, you can show in differential privacy that ensuring differential privacy alone incurs a fundamental loss cost. So this is the one on the right here, rho dp. This is the fundamental training loss that you must be paying if you ensure epsilon delta differential privacy. If your model dimension is D, if the number of workers in the system is N, and if each worker has M data points. So essentially, you pay the dimension of your model, which can be extremely huge. You pay something inversely proportional to your privacy level. So the more privacy you have, the worse this is. And you can hope to reduce this term if you have enough users in the system, or if each of these has a large number of data points. This makes a lot of sense. This is well known prior to our paper. Now, the interesting part also, as I explained earlier, is that Byzantine robustness, you pay also fundamental cost, which is driven by the heterogeneity, the data heterogeneity, amplified by the fraction of Byzantine workers. Now, this really suggests the question: what if we want to simultaneously ensure differential privacy and Byzantine robustness? Do we simply say, do we simply pay just the addition of those kind of two fundamental costs, or is there something there is some interplay, is there some trade-off between the two? That's what we observe. Actually, we show no matter what training algorithm you use, you must be paying a coupled cost between differential privacy and Byzantine robustness, which is essentially the cost, the dimension-independent privacy cost of a single worker, amplified by the fraction of Byzantine workers. Okay, and the intuition behind this results is pretty simple, actually. Sorry, the intuition is pretty simple. Essentially, we know that Byzantine robustness is hard because of heterogeneity, but because you're trying to enforce privacy, for example, by adding Gaussian noise, let's say, then you're kind of creating some artificial heterogeneity in your system. You want to make your gradient different from what it actually is, which on the whole system looks like some kind of heterogeneity between the gradients, between the data of the honest workers. And this is why the Byzantine adversary can exploit this kind of artificial heterogeneity to send even further gradients than they could if you were not trying to enforce privacy. Okay, so this is kind of the intuition behind this result. And we not only show that this is a fundamental cost, we also show that there are specialized algorithms dedicated to ensuring privacy and robustness simultaneously, which which have optimal guarantees, meaning that their convergence guarantee matches the lower bound as just showed now, up to constants, of course. And the algorithm is once again a variant of distributed gradient descent. So right now, the difference is that, of course, the worker injects Gaussian noise to their gradient to enforce local privacy. They update their local momentum, okay? And the server aggregates momentums with a special robust aggregation rule, and then it just makes it the usual update. And this special aggregation rule, it's what we call SMEA. It stands for smallest maximum eigenvalue averaging. And the guarantee it preserves is actually makes a lot of sense. So what it says is that the output of SMEA, this aggregation rule, is close to the true average gradient. And the error you make can be controlled by the maximum eigenvalues of the covariance of the honest gradients. And the trick is that because you will be using Gaussian noise is isotropic. So it's the same noise more or less in all directions. Because it's the case, then this is a much better quantity than having, let's say, the trace of this covariance, meaning that the dimension term will not appear in the final convergence bound. And this is exactly what the lower bound was suggesting, meaning our lower bound was tight. And if your algorithm leverages this isotropy of the Gaussian noise, then you can achieve a tight bound. A final observation in practice is that if you're in very high dimensions, if you think of really large models, and you're in a system which is relatively small in such a way that the Byzantine fraction, the number of Byzantine machines in your system is actually smaller than the dimension, then by using such dedicated algorithms, then you can make sure that the coupled costs that you pay because of differential privacy and Byzantine robustness is actually smaller than the cost you pay by differential privacy alone. So this is to explain why this bound is really good. It's because in high dimension, this term is really negligible compared to the differential privacy fundamental costs alone. So if you want to know more about this, you can check out our archive paper, the research of which appeared in the last ICMM. And I can take questions now.
Thank you so much, Youssef, for this great presentation about trustworthiness in AI and about privacy and robustness. So we have a lot of questions here from the audience, and I will start with the first one where a participant is asking why in distributed SGD, we usually take a mean and not a median, which is more robust.
Okay, so that's a good question. So you're asking, even if you don't have adversaries in your system, why wouldn't you use a median instead of an average?
Yeah.
So that's so you could try it out. Well, we already tried it, and it's not as good as an average, for the simple reason that for very simple problems, if you think of minimizing quadratic functions, the minimum of a sum of quadratics is an average, and so the solution should you should be averaging your gradients in a way to get to the solution. So my answer is there are simple problems for which you cannot do better than averaging gradients.
Okay, clear. Thank you. Thank you for the answer. We have another question from Ayman. So he is asking, is there an aggregation rule that is better than all the others and against all state-of-the-art attacks?
Yeah, so there, I'm not sure there is some best aggregation, but we've had a work where we show that if you can pre-process the gradients in a way that you reduce heterogeneity, we call this mixing, like mixing gradients kind of, then no matter what robust aggregation you use, you will get very good results. So I'm not certain there exists some kind of best aggregation, given that you can do such operations. Yeah.
Okay. Thank you. So we have another question. It's about the second part of the presentation. A participant is asking, how many Byzantine attackers are needed to affect heavily the training of a big model? Is only one needed or more?
So one would be enough, obviously, if you're doing, if you're not taking any precautions, if you're using averaging. But if you're not, if you're let's say using a median instead of averaging your training algorithm, then it would depend on the task you're doing. So if you're doing a harder task, let's say, I don't know, you're doing CFAR 100, you'll pay much more than doing MNIST, and it depends also on what kind of heterogeneity you have in the system. If, for example, on MNIST, each user only has, let's say, one label, they don't have some representative sample of all the data set, then even one worker can do a lot of damage in a relatively small system. Yeah.
Okay, so we have to watch out for Byzantine attackers.
Yeah.
We have another question. It's more general question. So we have a participant asking, what are the prerequisites needed to work in distributed machine learning? And if you have any book that you can recommend or particular course.
So it depends what you are interested in when you mean distributed machine learning. If you're interested in federated learning, there has been a lot of research going on, and there are many great surveys that you can easily find on the internet. And you can also refer to the papers I mentioned and the references in there to know more about the good references for distributed machine learning, either for robustness or without robustness, let's say just performance. And you can find references in the papers I cited. Yeah.
Okay, clear, thank you. So for sake of time, we will take the last two questions, and I'm sure the audience have many questions that they can ask in the breakout rooms. So we have a question about the practical fields. Where can we apply those findings practically, and from where can we benefit from it? And can we work be related to neural architecture search, and what is the practical fields in general?
Okay. In terms of practical applications, so as I explained, federated learning is already deployed. It's been deployed for a couple of years by so many companies, including the biggest ones. And they not only like deploy federated learning, the vanilla version, but they also improve it with privacy and robustness. Okay. They actually use differential privacy. If you look at a company like Google, they have a lot of research about making differential privacy private, differential privacy amenable or compatible with federated learning performance. And so that gives birth to so many use cases if Google uses it, right? Now, regarding robustness, it's still theoretical at this point. I mentioned that there are very simple algorithms that give you robustness, but we cannot yet compete with vanilla, or let's say non-robust distributed machine learning, because there is more research to be done in devising faster algorithms and devising or simpler algorithms and the likes. So privacy is definitely something that has many use cases already and that you can apply. Robustness is the main efforts right now require our research efforts, and it's not yet deployable, in my opinion.
Okay, thank you for the clarification. And we are looking forward to see all the practical fields of robustness in the future. So we will move to our last question in this Q&A session. The last question from a participant is asking about the code. Is there any code accompanying your paper where we can find all those implementations?
We do provide code. You should check out the paper, or you can also reach out to me if it's not entirely clear what the code is. But yeah, it should be somewhere in the paper.
Yeah.
Yeah.
Thank you very much, Youssef. So I encourage the audience to go and read the papers and check also the code for further information. So now we can move to our breakout sessions. So we have 2 sessions. The first one is Ask Me Anything with our guest speaker, Youssef Allouah. And the second breakout session is Discuss your deep learning project.